Welcome to today's video on chi-squared test. Chi-squared test is one of the most commonly used non-parametric test. So let's see what is a non-parametric test. In the case of parametric tests like t-test, etc., they follow certain assumptions like data should be normally distributed, data in each group should have approximately equal variance, etc. Chi-square test does not follow these assumptions and hence it is a non-parametric test. This can be used for hypothesis testing in data of categorical variables. Categorical variables are those that allow us to assign categories. For example, gender is a categorical variable, race is a categorical variable, occurrence of disease can be a categorical variable. We can have two categories, those who have the disease, those who do not have the disease. And this test is based on seeing the significance of difference between observed and expected frequencies. Observed frequencies are the frequencies which we collect as a result of our research. For example, suppose I am doing a research on occurrence of a disease, then I will have the number of people who have the disease, the number of people who do not have the disease. And this is the observed frequencies which I get. Expected frequencies are theoretical frequencies which we calculate, and these theoretical frequency calculation we will see when we move to the problems. The formula for calculating the value of chi-square is given as O minus E the whole square divided by E, where O, as we know, is the observed frequency, that is which we get as a result of our research, and E is the expected frequency, a theoretical frequency which we calculate. As we have seen in the tests of significance, we will compare the calculated value with the table value at a level of significance 0.05 with the corresponding degree of freedom, and we will see if the calculated value is greater than the table value. If the calculated value is greater than the table value, the null hypothesis will be rejected. If the calculated value is less than the table value, the null hypothesis will be accepted. This we have already seen under the tests of significance. Going to the data requirements for chi-square test, as we already know, it is done for categorical variables. So you should have one or more categorical variables depending on the type of chi-square test which we are performing. We should have independence of observations. That means the categorical variables should not be paired in any way. It should not be a pre-post measurement, etc. And we need an expected frequency of minimum 5 in each group. There are two main types of chi-square tests which are utilized in life sciences. The first one is goodness of fit test. This is suitable for genetics experiments where we already have the expected frequency based on some a priori hypothesis. For example, if it is a monohybrid or a dihybrid cross, we know that the ratios are 3:1, 9:3, 3:1, etc. So we will compare our observed frequency with the expected frequency which we already have, and we will decide whether the data is in line with the Mendel's law or it is deviated from the Mendel's law. The next test is test of independence. This is usually done to test the efficacy of a drug or efficacy of a vaccine, etc. Where we will have two categorical variables. One is the occurrence of the disease, which has two categories: no disease, having the disease. Other one is the vaccination. For example, if we are studying about the efficacy of a vaccine, whether they are immunized or not immunized. We will try to see if there is any type of dependence between these two categorical variables. Is there any type of association, or they are completely independent? So based on that, we will decide whether the immunization is effective or not. So let us see how we can do the chi-square test using Excel. So first we will go to the goodness of fit test. Suppose this is the data that we have got. We have performed a dihybrid cross, and in F2 generation, you know, we will have round yellow, round green, wrinkled yellow, wrinkled green, and these are the number of plants that we have got. So the total number of plants which have been studied is 224. Now we have to see the expected frequency. As we already know, the expected frequency is based on a prior hypothesis. So we know that the ratio is 9 is to 3 is to 3 is to 1, which means out of a total of 16, 9 plus 3 plus 3 plus 1, 16. Out of a total of 16, 9 have to be round yellow. So in 224, how many should be round yellow? So you have to calculate that and you have to put it here. You can actually calculate it by in Excel itself, equal to 9 divided by 16 into 224. So it is 126. So like this we can calculate the expected frequency. And the you do 3 by 16 into 224, you will be getting 42 in both these cases. And 1 by 16 into 224, you will get it as 14. So now we have to see the difference between the observed and expected frequencies. So instead of doing the formula manually, we can use Excel. And as we have already seen in many of our previous videos, we can go to the insert function options and you can choose the specific test from the drop down menu under statistical test. Another way of doing these tests is you can type the name of the test. When you start typing, you have the list of tests that begin with those letters. So from this, you can choose the respective tests also. So I am choosing chi-square test from this. So when I double click, I have the method in which the data has to be given. So I have to open a bracket and you have the actual range. Actual range is the observed frequency. So I have to select these observed frequencies, then comma. The next one is the expected frequency. So I have to do the expected frequency and then close the brackets, enter. So now I have got a p-value of the chi-square test directly, which is 0.65. So 0.65 means it is greater than 0.05, which means that there is no significant difference. If you get a p-value less than 0.05 or less than 0.01 or less than 0.001, we say there is a significant difference at what percent level of confidence, 95%, 99%, 99.9%, etc. But our p-value in this case is greater than 0.05, which means there is no significant difference. There is no significant difference means what? The null hypothesis is true. That means our data is aligning with the Mendel's experiment. So instead of calculating the chi-square parameter, directly we get the p-value based on which you can come to a conclusion about the data. The next one, let us move to an example of this test of independence. So we have taken a very simple 2 by 2 table in this case. So suppose with in a total of 300 people, this research has been carried out, and out of 140 people who were immunized, 110 did not get the disease, 30 got the disease, and out of 160 people who were not immunized, 100 did not have the disease, 52 had the disease. So this is the data which we have collected based on our research. So this is the observed frequency. So we have all the totals here, row and column totals. Now we have to calculate the expected frequency. So this is not based on any a priori hypothesis. So it has to be calculated assuming again, as such we said, if the null hypothesis were true, what would be the values? So what is the null hypothesis in this case? The drug is not effective in curing the disease, or the vaccine is not effective in preventing the disease. So we calculated by the corresponding column total into row total by grand total. So for this particular cell, it should be, the expected frequency will be this column 218 into this row total 140 divided by 300. That is what I have indicated here. What is the logic behind this? Whether they are immunized or not immunized, 218 people out of 300 did not have the disease. That means in 140, how many will not have the disease? This corresponds to a null hypothesis where we think there is no connection between the two variables or the 100. So I hope this is clear. It is the corresponding column total into the corresponding row total divided by 300. So for the first one, it is this column total is 218, row total is 140. So 218 into 140 by 300. For this, it will be 218 into 160 divided by 300. For this, it will be 82 into 140 divided by 300. For this cell, it will be 82 into 160 divided by 300. So, this is how the expected frequencies are calculated. The answers that we have got 102, 38, 116 and 44. So, this same total will be retained. Now, we can do the chi-square test as we have already seen. You can do it by typing the test. So you get chi-square test like this. We can do for all of the insert function options test. We can do it like this. So when you double click on chi-square test, you have to give the actual range and expected range. So this is our actual range, comma. Make sure that we don't give the totals when you are giving your data. Then this is the expected frequency and now enter. Now you are getting the p-value. This p-value is less than 0.05. That means there is a significant difference between the observed and expected frequencies. So if there is a significant difference, what do? We reject the null hypothesis. That means there is a significant association between immunization and disease. That means immunization is helpful in preventing the disease. In our next video, we will see about regression analysis. Thank you.